Tonight's speaker is our own Peter Lloyd. I say our own, grateful that Doncaster Astronomical Society allows us to share him. Peter was raised in southern England. He's come up to Yorkshire, and he's getting all the traits of Yorkshiremen. I've noticed just recently his grip on his wallet is tightening through conversations on the society band. Peter is well known for his knowledge of the moon and how to photograph it. So, with tonight's talk, The Origin of the Moon, will you join with me in welcoming Peter Lloyd? Peter, over to you.
Well, thank you, Paul, for that introduction. Yeah, when Roy asked me to fill in tonight to replace the original speaker who's had to drop out for some reason, he knew I'd given the talk just about the week before to the Doncaster group, and he just said, "Would you like to repeat it for us?" Well, that was obviously the easiest thing for me to do, but I do want to just set just a little bit of background. Currently, the Doncaster Society has just 6 members who were members before the COVID lockdown. The numbers, I'm glad to say, are building up again quite nicely, and there are now, I think it's currently 26 members. So that means there are about 20 new members who've only joined us in the last couple of years. And most of those, not all, but most of them have more or less indicated that they've always had some interest in astronomy, but never had time to pursue it. And so now they've retired, or their kids have left home or something. Now they've got a bit more time. They thought they'd join the local society, which is great. But it does mean we're largely now a society of what I like to call novices. So I've been doing a series on the moon. And in fact, part 1 was a development of a talk I gave to the general public at Pottery Car ages ago, entitled "What You Can Learn About the Moon Without the Need of a Telescope." And that went down quite well at Pottery Car. I'm not sure that its expansion went down quite so well here. It didn't really last for an hour. But one of the members came up to me after and said, "That was just what I needed." So, well, that was nice. Part 2 was the talk I gave to you some time back on the origin of lunar craters. But I must have expanded it a bit, I think, because it was going to run for an hour and a half. So I had to chop the last third off, which was all the part about the different craters you get at different energies of impact. And so that was going to be at the beginning of this part. And I was very tempted to call it the Moon Part 2, Part 2. But I had to think of something else to fill in the second half hour. I thought, oh, I'll talk about the origin of the moon. I should be able to spin that out for half an hour. Well, when I stopped to think about it, I thought, well, the formation of the moon, if people are going to understand the ins and outs, the pros and cons of the various theories about where the moon came from, they really need to have a general idea of where the solar system came from. So I thought, well, maybe I better just talk a bit about where the solar system came from. Well, the solar system formed at the same time as the moon did. As the sun did. So that meant I'd have to talk about the origin of the sun and the formation of stars in general. And that would inevitably bring up the idea that the sun is a 3rd generation star. So what the heck does that mean, and why is it important? Well, that takes us back to the formation of the elements. And if you're thinking at this point, oh God, he's going to talk chemistry. No, the formation of elements is not chemistry. It's nuclear physics. And believe me, I'm no nuclear physicist. So anything I say on that subject is read straight off the autocue. And that, therefore, takes us back to the primordial gases. What were the original substances from which the elements are made? And they're made in stars. So that makes it of astronomical interest. Well, the primordial gases, there was danger there of taking me back to the origin of the universe. And I really didn't want, and I don't want to talk about the origin of the universe. I tend to get myself into trouble when I do that. So I'm going to take the attitude that astronomy is a science. So, so for tonight, at least, we're all scientists. So we have to believe the scientific story about where the universe came from. And that says that 13,770 million years ago, the universe just popped into existence as an infinitely small, infinitely dense, infinitely hot blob of space-time, and it's been expanding and cooling ever since. And the people who developed that theory seem to know when things happen to an amazing degree of accuracy. However, what they do tell me is that 379,000 years after that initial act of creation, the Big Bang as we call it, the primordial gases were formed, and they were 75% hydrogen, 23% helium, and 2% lithium. And you may reasonably ask, what the heck was the universe doing for 379,000 years if it hadn't thought about getting around to making some atoms? And the answer is it was cooling down, because atoms can't form if the temperature's above, I'm not sure what, it's a few thousand degrees. It had created all the subunits of atoms long before, the protons, the neutrons, the electrons. Those had been created in about the first 2 minutes, but it couldn't assemble the final thing because the proton can't attract an electron until the temperature falls to, I think it's somewhere around 4,000 degrees. Now, I should say at this point that there is some risk. Well, in the next part of my talk, I'll be overlapping to some extent with the things that Phil Bull was talking about a few weeks ago. And I want to make it clear that if anything I say differs from anything he said, there is, I estimate, a 99.9% recurring chance that he's right and I'm wrong. But it doesn't really matter, because I'm interested in the wood and how the wood fits into the landscape, the general landscape. And if I say the wood is full of oaks and he said it was full of ash, it really doesn't matter. I don't care. So we have the primordial gases. So if we look at those, where did the elements come from that built the Earth and us? I can guarantee we are composed of an awful lot of hydrogen. Don't quote me on this, but I would think probably on an atom count basis, we're probably more than 50% hydrogen, because it's in all our proteins and our carbohydrates and all that stuff. I can guarantee we don't contain any helium, and I sincerely hope that none of us contain any lithium, although I expect we've all got a lump of it in our pockets, because of course it powers our mobile phones, our laptops, our electric bicycles, our electric cars. Everything these days seems to be powered by lithium. Well, you need, the elements are formed in stars. That's what makes it of interest to astronomers. And you need gravity to make stars. Now, at this point, I was going to say that gravity is a very strange force. But then I've realized I can't really say that, because there are only 4 fundamental forces in nature. And 2 of those are confined to the atomic nucleus. So out here in the macro world that we live in, there are only 2. There's gravity and electromagnetism. And you can't really say that one of those is ordinary and the other one's strange. They're certainly very different. And gravity has some very important properties that make it what it is. First of all, it's always attractive. There's no such thing as negative gravity. It always pulls things inwards. Secondly, the force is independent of the motion. It doesn't matter how the object is moving, the gravitational force on it will be the same. And we know that from everyday life. I mean, if you jump off the bottom step of your staircase at home, assuming you have a staircase at home, And as long as you flex your knee slightly, you won't notice the bump when you hit the ground. But jump out of a first floor window and land badly, and you might twist an ankle or even break a small bone in your wrist, I suppose. And if you climb up a ladder to clean out the guttering and you fall off there, you're likely to break a leg. And if you jump off the balcony of a fifth floor room in a big hotel or off the balcony of a flat on the fifth floor, you probably kill yourself. And that's solely because as you fall, gravity goes on pulling you, you go faster and faster and faster, and the faster you hit the ground, the more the bump. Finally, if you give in to gravity, it gets stronger. I like to describe that as the mafia effect. Now, there is a fourth thing that I didn't put on here, and that is that gravity can act over huge distances. But that really amounts out of the fact that it's always attractive. The electromagnetic force, in theory, can act over large distances, but in practice it doesn't, because anything that's attracted to one pole is repelled from the other, and the further away you get, the less is the difference between them. Oops, sorry. So, the formation of the elements. They're formed in stars, and that a lot of that early work, of course, was originated by a well-known Yorkshireman, one Fred Hoyle, who started off an awful lot of this stuff and worked out a lot of how the actual nuclear physics went. And I actually have a book by Fred Hoyle, and I started reading the chapter involved, and frankly, I didn't understand it, so I gave up. Now, stars are a big ball of gas, and gravity is trying to squash it down. And it succeeds up to a point. But eventually, when it gets to a very high density and a very high temperature at the center, then nuclear reactions start. And the first thing that happens is you get 4 protons fusing together to form the nucleus of the atom helium. It happens in 2 stages. The temperature is such that in the center of this, it's a collapsing cloud of gas. In that center, you've got mainly protons, some protons and neutrons combined to form deuterons, and they're flying around like anything in a sort of sea of electrons. And at that stage, the protons don't collide with each other because they carry a positive electric charge, and so the electromagnetic force keeps them apart. They come in together, but it wings off, and you want to experience that, just take 2 magnets and try and put the common poles together, and you find they keep pushing you away. But gravity doesn't give up. The temperature goes up, the density goes up, more and more packed in, moving around faster and faster, till eventually the 2 protons approaching, the mere inertia of their movement overcomes that electromagnetic force. And they don't exactly crash into one another, but they come up and they touch. And when they touch, the strong nuclear force, one of those other fundamental forces I mentioned, cuts in, grabs the 2, pulls them together. One of the protons kicks out a positron. Now, a positron is exactly the same as an electron, but it carries a positive electric charge. And it turns it into a neutron. So you now got this thing. It's still hydrogen because it's only got 1 proton in the nucleus, and that's what determines what element it is. But it's a heavy form, and the particle is usually called a deuteron, and the gas is called deuterium. But anyway, 4 of those combined, or 2 of those combine to form 1 atom of helium with a mass of 4. Now, this is the crucial point. That atom of helium weighs very slightly less than the 4 atoms of hydrogen that created it. And Einstein tells us that mass and energy are 2 sides of the same thing. So that loss of mass comes out as energy, but via what is probably the best known equation in the whole of physics, E equals mc squared. So this small loss of mass, and it's, I don't quote me, but I think it's 0.4% is all that is lost. But that small amount of lost matter is turned into energy by multiplying it by c squared. Now, c is the speed of light. It's a very big number. So c squared is a ginormous number. So actually a huge amount of energy comes out. Now where does that energy go? It causes the core of what is not quite it's just forming a star at that point. It causes that central core to heat up even more than it was before. And hot things like to expand. So we've now got an opposing force which is stopping the gravitational collapse of the cloud, and that's when the star lights up. Now, that's the situation that the sun is in at the moment. It's fairly easy to see that you get a nice balance set up, because if gravity tends to win a bit, the speed of this reaction goes up, more energy is produced, it gets hotter and expands again. If this tends to win, it expands, the core expands slightly, it cools off a little bit, and the rate of energy production drops. So you very quickly get into this equilibrium state. And as I say, that's the situation that the sun has been in for about the last 4,000 or 5,000 million years. And at that time, it's believed to have burnt through about half of its supply of hydrogen. So the sun's good to go for another 4,000 million years or so. But when the hydrogen really begins to run out, gravity starts to win, the core starts to collapse again, and now some other reactions can come in. The helium will start fusing together, and if you take 3 atoms of helium, they fuse together to form an atom of carbon. And helium has a mass of 4, so 3/4 of 12, so you get a mass of 12, and you get 3 to 6 protons, and that's makes it carbon. And again, the carbon so produced is a little tiny bit lighter than the 3 helium atoms that formed it, and energy comes out. Or you can have 4 atoms of helium fusing together, and they make an atom of oxygen. So that's another source of energy for the star. There is another reaction which, for simplicity, I didn't put on here. You can have 3 heliums and a proton merging, and they make an atom of nitrogen. So the star starts to make carbon, oxygen, and nitrogen, which are 3 of the most important elements as far as we're concerned. Okay, now in principle, the star can then work its way up this sequence, and the chemists among you will immediately notice that these are all the even-numbered elements, and their atomic masses go up by 4 at each step, because each one is adding a helium to the previous one. You get the odd number ones because nitrogen then is the source of all the others. Now, how far up this chain a star can get depends how heavy it is. And in fact, it's somewhat doubtful whether the sun will even get to this stage, because it simply isn't heavy enough. Because you've got to remember, in that central core where all this is going on, there are still electrons there. And electrons don't like being packed together too closely. And you get what I fully admit I don't fully understand, something called electron degeneracy pressure. And this is enough to hold up a star the size of the sun. So when that happens, this chain of reactions stops, and my guess is that the sun actually gets stuck at this stage. Now, this is generating an awful lot of heat and light. And the way in which energy leaks out of stars, the main inner part of the star is transparent. So the energy is transferred initially from that central core out by radiation through the transparent part of the sun. The outer layer, I don't know how thick it is, quite thick, it becomes opaque, so the energy can't get out that way, and it gets out by convection. It's heated from below and it convects up. And so when we look down on the sun, what we see, in fact, is the upper layer of this convective zone. And that's what gives rise to the sort of mottled effect that you can see on the sun. If you've got the right equipment. And in fact, you can mimic this quite nicely, actually. If you put a pan of water to boil on the stove, if you watch it just before it starts to bubble, you can see these pockets of hot water coming up, breaking on the surface and falling down. You can see this convection going on, and it looks very like the surface of the sun in some ways. Now, there's all this energy being generated in the center. So this is heating up the rest of the star, the rest of the sun, if we're talking about the sun, and that makes it expand. So in the distant future, in about, I don't know, 4,000 or 5,000 million years, the sun will begin to expand. It'll expand out to the orbit of Mercury. It will absorb Mercury. It will go on expanding till it gets to Venus, and it will absorb Venus. Quite whether it'll get to the Earth's orbit or not is a little bit uncertain, but it's become what's known as a red giant. And a red giant may be cool by stellar standards, but it's still very hot. So long before it will have completely frizzled the Earth, it'll have boiled all the water off, killed everything in sight, and the Earth will just be a dead hulk of a thing. And in fact, the Earth will have moved out in its orbit, because remember, the sun has been generating all this energy by consuming mass. So the mass of the sun has been decreasing, so its gravitational force will be decreasing, so the Earth will be moving out in its orbit. Excuse me. But in fact, it almost certainly will absorb the Earth, because there is what we now call the solar wind streaming out from the surface of the sun, and that will cause some drag on the Earth as it goes round, and so it'll almost certainly spiral into the sun eventually. Now all this, so what we've got now is this intensely bright object in the center, and a lot of very diffuse gas and stuff much further out, and in fact is being blown out. And we can see that, oh sorry, move past that. And we can see that in these things. This is a planetary nebula. We happen to be very lucky with this one. We're looking down the polar axis of the star, and here in the middle is the white dwarf that's been left when the main part of the star is blown out. And all this stuff goes out. It's got a lot of these elements in it that the star has made. They combine and they form other compounds. The intensely bright white dwarf at the center is emitting lots of ultraviolet light, which makes this material fluoresce, and you get these pretty colors. This makes it look as though the stuff is being pushed out as a ring. It's not. You would think it would go out as a sphere, and it doesn't do that either. It goes out as a sort of donut shape. And I'm sorry I haven't got a picture, but there's a thing called the Dumbbell Nebula, which is the same thing but viewed more on the equatorial plane. And you can see then that there's a sort of it's a much more bulbous object in two lobes, one on either side, and that indicates that really it's coming out as a sort of donut shape. So we go back to this series. If the star is heavier, about 1.5 times the mass of the sun, then the electron degeneracy pressure is not adequate to support it. So the compression goes on, and the star gradually works its way up this sequence. Every step here generates energy. but every step generates rather less energy than the previous one did. So these reactions start having to go faster and faster in order to generate enough energy to keep the star alive until you get to iron. That's fine. But when you get to iron, you've run out of this, because sure enough, if the star has started creating iron in its core, and incidentally, every time it starts one of those reactions, it starts it right in the center of the core. The outer parts of the core are still generating the earlier reactions. So the star has become almost like an onion, with layers of all these reactions going on, right the way back to an outer layer where the hydrogen is still fusing to form helium. But when this last reaction gets to the point where it can no longer support the star, gravity cuts in again, of course, compresses the core again, and the iron starts fusing into the higher elements. Now here's the problem. These higher elements are actually heavier than the iron and the helium, which are fusing together to make them. So that means that energy has to be provided to make them. So suddenly, what had been a furnace at the center of our star becomes a refrigerator. It actually cools the center. So now the center collapses because it's no longer generating any power at all. That means the next skins out are now no longer being supported. They all collapse inwards. Their nuclear reactions all go completely out of control, and the star literally blows itself apart. And that's when that's what you get 1,000 years after such a star explodes. This is the Crab Nebula. I'm sure you recognize it. And this, of course, is now distributed all those lovely elements back out into the solar neighborhood. So when it came to the sun, I should add that once these things are out in space, they cool down very rapidly. You've got all the elements there, all sorts of chemical reactions start occurring, all sorts of other compounds are made, including a lot of there are metals, there are silicates and oxides and all those sort of things. And they form little particles of dirt. Astronomers call them dust. And you can see that in pictures of this sort, where you get these dark nebulae, which are full of this dust which obstructs the light. And what we have here is an emission nebula at the back, which is fluorescing hydrogen, giving out red light. And we have this area in front of it where it's full of this dirt and it stops the light coming through. And I'm delighted to be able to acknowledge that this picture is a part of a much bigger picture of this whole area produced by Johnny and Rachel, forgotten your surname, and they really are masters of astrophotography. This is a tiny part of a superb picture of the whole area, which I'm able to select and expand to this size, and you still get this beautiful picture. So thank you, Rachel. Now, I've jumped ahead a little bit here. When the sun formed, I said it was a third generation star. So the cloud of gas that it formed from was largely hydrogen, quite a lot of helium, but also quite a lot of these higher elements. So when that cloud collapsed, all these dust particles and things were included. Now, that cloud must have been rotating. You may say, why must it have been rotating? Well, if you think about it, you've got this big cloud, I don't know how big it was, a couple of light years across or something, full of billions upon billions upon billions of particles. all moving around randomly in all sorts of directions. Now, you can always resolve any motion into two motions at right angles. So we can resolve it into a motion towards or away from the center and at right angles with that, which is a tangential movement. Now, if you're going to insist that that cloud is not rotating, you have to assume that if you add up all the tangential motions of all these myriad particles, it comes to exactly zero. And that is so unlikely. It's almost bound to come to, it may be a tiny, tiny amount, but it's not zero. And that represents a rotation. And as far as the solar nebula is concerned, we know that it was rotating because the sun is rotating. The sun is rotating very slowly. It takes, if I remember rightly, 26 days to go around once. And that's incredibly slow. I mean, any of you who've got telescopes with electric drives on them will know how difficult it is and all the low gearing that has to be put in the RA drive so it goes around once a day. And the sun's going around once in 26 days. It's incredibly slow. But if you then expand that into a cloud a light year or more in diameter, when rotating objects collapse or shrink, their rotation speed increases. I mean, you know the usual example of the ice skater who starts off on a graceful turn, gets on one leg, pulls her arms, the legs in, starts spinning ever so fast, and then opens the arms up, the spin decreases, and she comes gracefully out of the spin. Well, exactly the same thing happened with the cloud that was going to form the sun. It had this very slow, would have been fantastically slow rotation, but as it collapsed, that rotation increased till it got to the sun's size when it was once every 26 days, which isn't exactly much. But within that cloud were a lot of particles, dust and gas and all sorts of things. Some of them had sufficient tangential motion that when everything else was being pulled into the central zone and forming the sun, some of them had enough tangential movement to miss the sun and go into and swing round it and go into an orbit around it. And I wanted to try and illustrate that disk that formed around the newly formed sun. And this was the best I could find and steal from the internet. I don't think it's a very good example, demonstrating of it, but it gives you the idea. It makes it look like a ring, whereas it must have been a disk, because it must have extended from around about Mercury all the way out to Pluto at least. And it would be of these refractory compounds in little dust particles, it will be gases of all sorts. And if you think about that cloud, gravity doesn't like things like that. It's going to try and clump things together. And in the inner part of that cloud, it's really only the refractory materials which will condense out of the vapor phase. The silicates, the metals, the oxides, things like that. And these are the things that have formed those inner planets, Mercury, Venus, Earth, and Mars. So that's understandable. Further out, when you get to Jupiter and Saturn, the more volatile components are condensing, so they pick up methane, ammonia, water, carbon monoxide, carbon dioxide, those sort of materials condense out. And there's much more of that stuff than there is of the heavier elements. So Jupiter and Saturn grew very large by picking all this stuff up. And of course, they also got large enough in the end that they were able to grab hold of hydrogen. A lot of hydrogen in the atmosphere of Jupiter, for example. So they grew very massive. If you go further out, the even more volatile things like nitrogen would condense. And so for Uranus and Neptune, you get the ice giants and you go out to Pluto. And we know that the surface of Pluto is covered in solid nitrogen. And incidentally, to an astronomer, ice means any substance in its solid form which would normally be thought of as a gas. So it doesn't have to be frozen water. In this case, we're talking about frozen nitrogen. And indeed, the Triton, one of the satellites of Neptune, actually has geysers on it, but they're not water geysers, they're nitrogen geysers. They're liquid nitrogen being shot out. And of course, you've got the lovely example of Titan around Saturn, which has what on Earth would be called a hydrological circuit with rain forming rivers and ponds and evaporation into clouds, but it's not water, it's methane. Anyway, I should say that that is really a very naive explanation of why the solar system is as it is. Now we've got visions of the extrasolar planets. We know that there are a lot of hot Jupiters out there. These are big planets rotating close to their star where they couldn't possibly have formed. And it's believed that at some point, Jupiter and Saturn almost certainly migrated inwards, caused chaos, throwing stuff all over the place, and then by some mysterious force, they moved out back to their existing position. So it was no doubt more complicated than I've tried to make out. So at last, we can get to the formation of the moon. We now know where the solar system came from, and it's made of all these bits that coalesce together to form the planets. Now, in I suppose the first half, or a bit more than the first half of the 20th century, there were three competing theories about the way the moon formed. And they became colloquially known as the daughter, the sister, and the girlfriend models. It's been objected to lately that that's very sexist. Why don't we call them the son, the brother, and the boyfriend models? Well, you can if you like. Chuck Wood in his book even goes further and says they should be called the offspring, the sibling, and the significant other methods. I'm an old man, I've no chuck with this sort of stuff, so I should continue calling the daughter system the girlfriend models, or perhaps I'll be formal and call them the fission, the co-accretion, and the capture models. Now, the fission model was first expounded in detail by George Darwin, who was the son of the rather better known Charles Darwin, and was a very eminent scientist in his own right, although he originally qualified as a lawyer, but he seems to have been a very clever chap who could do almost anything, and he did end up with a chair of astronomy at Cambridge. And he proposed this idea that in the early stages of the Earth, it had become liquid, and there's no doubt the Earth was liquid at one time because it's a differentiated planet. The heavy materials, the iron, has sunk to the center, and the lighter silicates and oxides and things have floated to the top, and that's what we live on. Now, he believed that the Earth formed as a prolate ellipsoid. That's a sort of egg shape stretched out a bit, and that it was rotating about a minor axis. Sounds crazy to us now, but that was the idea. And he proposes that something, he doesn't say what as far as I know, caused the rotation rate of the Earth to increase. And it got to something like 2 hours a day. That caused the object to stretch out into a sort of elongated sausage. And eventually it got so fast that a blob detached itself from one end, went into orbit as the moon. Then he proposed that the same tidal friction that's going on today, slowing the rotation of the Earth and pushing the moon further away, acted to slow down the rotation of the Earth, push the moon further away to get us to the stage we're at now. There's all sorts of things wrong with that idea. We don't believe that the Earth would have been formed as a prolate ellipsoid any longer. It wasn't so unreasonable for him, in fact, because there was a theory going around which was only developed a few years after he came out with this one, but where the thought was that the planets were formed by a protuberance pulled out of the sun by a passing star, and that this was pulled out into a long sort of cigar shape, which detached itself from the sun, was caused to rotate about its long axis. It then broke up into the individual bits and pieces that made the planets, and those turned out to be this ellipsoid shape rotating about its short axis. So for Darwin, it wasn't so daft. But even if you take today's idea where the Earth is more like a spherical liquid object as it differentiates, if something was to cause it to spin hard, it would stretch into a disk and the outer edges might detach, solidify as lots of little bits, so the Earth would have a ring which then gradually accumulate to form the Moon. And we do know that the Moon almost certainly did form, or at least the latter stages it formed by bits raining down on it. That's where all those craters come from. And that would not be accounted for on Darwin's idea. So possible, but extremely unlikely. So the fission model really doesn't stand up. The co-accretion. This assumes that the Moon formed at the same time as the Earth did in the same vicinity, and that the Earth was a sort of double planet, but one piece was significantly smaller than the other, and it became the Moon, and the two were created side by side. That doesn't really work, because if that were true, you would expect the two objects to be made of the same stuff, and they're not. The mean density of the Earth is about 5.5. The mean density of the Moon is about 3.3. It's made of different stuff. The Earth has this big metallic core, the Moon doesn't. Probably doesn't have a metallic core at all, but if it does, it's a very small one. So really that scuppers the co-accretion idea. So lastly, the capture theory. This just assumed the Moon formed somewhere else out there in the solar system. It wandered around and it happened to get a bit too near the Earth, and it was captured into orbit around the Earth by the Earth's gravity. The problem with that idea is it wouldn't happen like that. If you follow the antics of the space people, you know that if you send a space probe out to Venus or something and you want it to go into orbit around the planet, it's no good just sending it there. It'll come into the gravity of Venus, it'll swing round in a parabolic orbit and disappear off again. And you have to put an engine on board which fires to slow the spacecraft down, so then Venus can capture it and then go into orbit. Well, if you imagine the Moon coming in and being captured by the Earth, how did it lose energy? There's really no mechanism for it to lose energy. You can say, well, maybe it plowed through the atmosphere, lost a bit of energy there. Yes, all right, it could have happened. In which case, if it lost enough energy, instead of going off to infinity, it would go out to a long elliptical orbit, out to an apogee, that is the point most distant from the Earth, which is quite a long way up, but it would come down, and it would always come down to the same perigee distance. And if it plowed through the atmosphere again, it would lose more energy, and it would go up slightly less. So the apogee would come down, but the perigee wouldn't go up. So eventually the apogee would come down till it was inside the atmosphere. The Moon would spiral in and be absorbed by the Earth. So that doesn't work. You could say, well, maybe in the first pass or two through the atmosphere, the Moon blew away an awful lot of the Earth's atmosphere. So when it came down again, it didn't slow down. Well, all right. But then you've got to explain what brought the apogee down and sent the perigee up to get the Moon into its roughly circular orbit it's in now. And it's almost impossible to work out how that could have happened. The only possibility I can see is that if the Moon was a double object when it came in, then one of those objects could lose energy to the other. That would stay in orbit as the Moon, and the other one would be shot off into space, never to be seen again. Well, possible, I suppose. There are asteroids with satellites which may have formed that way, but on the whole, we don't get double planets knocking around, so not very likely. So really, none of these. Oh, and there is another quite important thing that scuppers the capture theory. The evidence we have from meteorites and from samples brought back from the moon, but mainly from meteorites, indicates that different objects in the solar system have different ratios of the isotopes of the elements, particularly oxygen. Oxygen can consist in two forms, oxygen 16 and oxygen 18. They're both oxygen. It's just that oxygen 16 contains 16 particles in its nucleus. Oxygen 18 contains 18, contains 2 extra neutrons. And the physicists can distinguish these very easily and measure them. And when they measure them in meteorites coming from different places, they are different. We don't know why, but it looks as though different parts of the solar nebula had different ratios of these elements. And it's been done for more than oxygen, and they're all that little bit different. But of course, we've sent astronauts up to the moon, they brought samples back, and they've been analyzed very accurately, and the isotope ratios in the moon are exactly the same as they are on Earth. Well, I say exactly. Apparently, if you really go to the ultimate, they can detect a tiny difference, but it's a tiny difference compared with what we believe are varying in the solar system. And we even have a few meteorites that are believed to come from Mars, and they have a distinct ratio as well. So that really also scuppers the capture idea. So somewhere around the 1950s, I think it was, another idea came out known as the giant impact theory. And this suggested that the early Earth, after it had been liquid and differentiated and had at least begun to solidify, was struck by an object about the size of Mars, which was also differentiated and solidified. It was a slightly glancing blow, and that caused, of course, an enormous explosion, which scattered an enormous amount of material out. A lot of it, no doubt, was lost forever, but some of it went into orbit to form the moon. The rest of this object, and they were very clever, they gave it a name. They called it Theia. And that was a very good name, because Theia in Greek mythology was the mother of Selene, the moon. And there's nothing like giving a thing a name to make it believable. So they're very clever. Well, that is currently the preferred model. However, it doesn't really fit the bill either. And I'll show you more detail in a minute. But on the matter of the isotopes, if Theia was formed elsewhere in the solar system, one would expect it to have different ratios of the various isotopes from the Earth. So the only way you could get the Earth and the moon with the same ratios would be if exactly the same ratio of Earth and Theia went into the moon as went into the Earth. And that seems so unlikely. Possible, maybe. One extra piece of information that's in favor of it, which I've only discovered quite recently, but it's been known for about 20 years. The geologists knew about it. I don't know whether it got out to the astronomical community. Below Africa and below the Pacific, there are two blobs of material sitting on top of the solid iron core of the Earth. Nobody really knows what they are, but it has been suggested that they are two pieces of the iron core of Theia, which was absorbed by the Earth, shattered into two, went down, and has failed to merge with the solid lump of iron in the center of our planet and causes these two lumps. Having produced this screen at this point, I felt I needed something to fill in over here. thought about it quite a lot and decided that maybe wife would fit. Now, if you want to, you can call it husband, or if you like, you can call it spouse. Whether marriage is a giant impact, I will leave for you to decide. So, now in Chuck Wood's book, which is fairly old now, it was published in 2003, I think, he publishes this table, which was originally produced by John Wood in 1986. So that's even older, I'm afraid, but I don't know if anybody's done this since. And what he's got here is all the properties of the Earth-Moon system that need to be satisfied by whichever model you want to say. And what John Wood did was to provide each of these with an exam score as to how well it accounts for the mass, the angular momentum, all this stuff. And it really makes for quite interesting reading. What Chuck Wood did was to give each of these letters a numerical value, A equals 4, B equals 3, and so on, down to F equals 0, F being failed. He averaged them and then converted them back into a grade again. And lo and behold, yes, the impact theory does best, comes up as a B+. Only a B, it's not an A. And if we look up, you see that it has 2 A's. It accounts, it's physically plausible, and it allows for a magma ocean on the moon. And we know that there almost certainly was a magma ocean on the moon at one time, because it has erupted onto the surface and forms the great lava plains, which are the barrier on the moon. And so there was a magma ocean, and it's an orthosite is a light-coloured rock. We simply float it to the surface like a scum. So it accounts for that very nicely. The oxygen isotopes, he gives it a B. Well, I'm not sure I would, but there we go. It doesn't account for it very well. The depleted volatiles, the moon is depleted in the more volatile elements. The surface rocks have very little water in them, and there's various other volatile materials that are simply not there. And this is what you'd expect if the moon had been very hot at some stage. And it counts for it not too well, but it does. The angular momentum is the sum of the angular momentum of the moon in its orbit, the moon's rotation, and the Earth's rotation. And angular momentum is something that's conserved. So somehow the momentum we see has to be provided to the Earth-Moon system in some way. And John Wood felt that it didn't do a terribly good job, but it was not too bad. But notice there are 2 I's. I means insufficient information. So he couldn't decide whether the moon's mass was well or poorly indicated by the impact, or the depleted iron. There's less iron in the moon than there is in the Earth. He felt there wasn't enough information. And it does seem to me that the figure you get down here will all depend on what goes in here eventually, because here we're averaging only 5 items, whereas on the other ones we're averaging excuse me, we're averaging 7 of them. 2 A's and 3 B's, so B+ is reasonable. But now if we look at the fission, that has 3 A's. So it does better than the impact in that respect. Unfortunately, it has 2 F's, and that's what really scuppers the fission. The angular, you can't account for the angular momentum by a long way, and frankly, it's physically implausible. Fair enough. The worst case is the capture model, which is perhaps unfortunate, but that's because it gets a D- for physical plausibility. It's just about plausible, but most unlikely. It gets a D for the plasma ocean, because why on earth would the moon form a plasma ocean if it was formed like any of the other planets? And he gives it a B for oxygen isotopes. Well, you know, they would expect it to be different, but maybe not a lot different. It fails on the depleted iron. It doesn't do too well on the volatiles. Why should the moon have lost the volatiles when the Earth didn't? And it's none too good on the angular momentum either. Interesting, the co-accretion scores almost exactly the same as the fission. It only has one A. Gaussian isotopes is the only thing that John felt it really worked, but it was fairly bad on some of the other things. So in my personal opinion, the value you get here is going to be very dependent on what comes in these two places. If they come in as A's, this will come up to an A and it's clinched. If they come up as C's or D's, this will come down to be a C and will be no better than the rest of them. So that's why I always get a little bit cross when I hear people say that moon was created when an object the size of Mars collided with the Earth. Well, it's the best idea so far, but it doesn't really answer all questions well. There have been, since it was originally proposed, various variations of it, and I'm afraid I haven't followed those in any detail. But various people have suggested slightly different versions of it. For instance, that it wasn't Theia colliding with the early Earth. It was two objects like Theia colliding, merging, mixing, coming apart as two bits that cause that sort of thing. But the impression I get is that the variants to that theory which improve one of these, sorry, I'm pointing to my screen, whoops, to improve one of these things tends to make another one worse. So I think it's still not definitive. It's the best idea we have so far, but probably not the answer. So the answer to my original question, where did the moon come from? I haven't the faintest idea. You have as much information as I do now, so you decide. Is the impact theory really what happened? It probably isn't really any of them, or not in the form they are. So there, on that slightly unsatisfactory note, I leave you. Thank you very much.
Peter, thank you for a very interesting and detailed talk. I'm sure that there are going to be a few comments and a few observations and hopefully a few questions. Could I ask you to stop sharing your screen, please? And we'll go back to the gallery.
Oh, I apparently have stopped it. So, well, Paul, as I explained before, I do sometimes have difficulty hearing questions from the floor, so I might have to ask you to repeat them because I can hear you very clearly because you're much nearer the microphone. But
well, that's because we've just been tweaking the way we do things here, and you're now going to be very disappointed as I go over to the mic. So you might actually detect a change in my tone. Could I ask somebody to turn on one of the banks at the back of the room, please? Banks of lights. So we're looking for questions or comments from online and from in the room, as usual. If you're online, please put up a digital hand. If you're in the room, as usual, pass any note of the realm to the front of the room, and I'll bring you into the conversation. You were talking about the moon not having a heavy core, but from the Apollo mission and from the original lunar orbiter missions was the discovery of mass cons in the moon, concentrations of mass that mean that the gravitational field of the moon isn't as uniform as one would expect, and that gives rise to difficulties in putting an object into orbit around the moon. Which of your three models do you think would best would best explain those mass columns.
Yeah, sorry, I'm not sure I quite heard everything you said there, Paul, but you're asking about the mascons. I don't know what they are. What I always assume they are the remnants, perhaps, of objects that have collided there and got them sunk down and were a little heavier. Whether they contain a lot of iron, I really don't know. They may just be a more dense material.
Right. Okay. I'm looking for questions. I've got nobody in the room. Oh, sorry, Graham.
I'm a little bit interested in the additional material on the Earth's core in the southern hemisphere. Is that thought to be iron or some other material?
Sorry, Paul, could you repeat that?
Graham's asking about the additional material found around the Earth's core in the southern hemisphere. And he wants to know if they're iron or some other material.
I don't know that, and I don't know whether anybody actually knows that. I mean, they've deduced it's there relatively recently, only in about the last 20 years that they even discovered it's there. And of course, it's done by mapping earthquake waves as they pass through the Earth. So they know something is there which is denser. Whether it's actually the same iron as the center of the Earth, I don't think is known.
Okay, great. Simon.
Yeah, I'd like to ask a question about the tides on Earth. We know the moon affects the tides, and we have one high tide facing the moon, and we have another high tide on the other side of the Earth facing away from the moon. I don't understand how you get the tide on the other side of the Earth. Can anybody explain that?
Sorry, Paul, I ought to hear people online, but I didn't hear that either.
Oh, I'll just translate that into English. And Simon wants to know about the phenomena of having a high tide on the moon side of the Earth and also having a high tide on the anti-moon side of the Earth at the same time. Why is there this double high tide going around instead of just one high tide on the moon side?
Oh, that's a nice one. Yes, thank you. What you've got to remember is that the moon is not rotating about the center of the Earth. The two objects are each revolving around what's called the barycenter. There's a center of gravity between the two objects. And that barycenter for the Earth-Moon system is actually inside the Earth, but it's, and you've got me here, it's nearer the surface than it is the center. It's quite a long way out. So the moon's gravity is pulling up the water on the one side, but you've got a sort of centrifugal effect that is causing the water to mound up on the far side as well. So that's why you get the two tides.
Okay.
Does that make any sense?
Yeah, I think Simon's happy with that.
Oh, good.
Thank you for that. Anybody else in the room?
Did Ed do a talk on that?
Ed Bottomley?
Yeah,
I don't remember.
some time ago, I think.
No, I don't remember. It's it was interesting you were talking about rotating gas clouds early on in the talk.
That one, sorry.
I'll just turn the microphone back. I think it's that one. How's that, Peter?
Oh, that's much better, Paul, yes.
Okay. So you were talking about rotating gas clouds.
Yes.
And Alfredo Caparetti, who we had about 3 weeks ago, he was talking about the discovery of a gas cloud a galaxy that was pure gas. It appeared not to have any stars in it. And one of the questions there was, did it have, were the spectral lines showing anything other than hydrogen and helium? And Alfredo at the time said he didn't believe so. So it was almost like a pristine primordial gas cloud from the Big Bang. And it would be interesting to see the ideas about rotation coming into effect. And I mean, we're not going to be around long enough. We won't have time to do the observations. But future generations might actually see those first stars forming out of those out of that gas cloud. So
yes, I managed to skate over how the very early stars formed, because I find it difficult to quite conceive how they would form when what you've got in the whole universe is a uniform, presumably uniform of hydrogen fairly uniformly throughout the universe. But presumably, the mere statistical fluctuations would cause some parts to become a little more dense than others. And once the temperature was low enough that things weren't flying around too much, gravity just managed to hold on to them. But
well, interestingly, Alfredo intimated that there was indications that dark energy and dark matter wasn't as dense in this gas galaxy, and that might have had a stunting effect on the evolution of the galaxy, which is an interesting thought, that dark energy and dark matter is lumpy through the galaxy. It's not uniform through it. So, but that's speculation.
Yes, I mean, I don't pretend to have any knowledge of dark matter or dark energy. I'm sort of, I suppose it exists, you know, and I can see the argument for the dark matter, that galaxies are rotating too fast to be accounted for by the matter we can see. I just think, well, why does everybody think we can see all the normal matter? But I'm not going to argue about it.
Okay. And just one other thing that Alfredo brought up, if I can remember the name of the system, he showed a photograph of a system called PDS-70, and it showed a solar system starting to form, and there was indications of co-orbiting planets in the same orbit. So your colliding object theory starts becoming a little bit more plausible.
Yes. Yes, I'd forgotten that aspect of his talk. Yeah, I mean, in principle, there's no reason why you shouldn't have two in the same orbit, so long as they're the Lagrange points.
Yeah. So whether they are at the Lagrange points, I don't know. I've not read that up. I'm usually very, very bad at remembering designations of stars and things like that. And the only reason that I remember that one is that the PDS is obviously my initials, and the 70 was the house number of my parents' house where I grew up. So that one's stuck in the head. Usually I'm dreadful at it. So I'm looking around for any other questions. Tony Morris. Tony, if you can shout at this show.
Can you hear me, Peter?
Just about, Tony, yes.
It's just when we image the moon, we can pull out some colour detail from the mineralogy of the surface of the moon.
Yes.
So if we discard the heavier elements that go into the core of the Earth, would the surface of the Earth without the atmosphere look similar to the surface of the moon?
Put it this way, Tony, the surface of the Earth has been so modified by plate tectonics and by life. I really don't know what it would look like if you stripped away all the life and all the atmosphere. Certainly, one of the major ones that differs on the moon is the basalt. And some basalts are more red, others more blue, and that's attributed to their titanium content. Basalt is in fact a very common base rock on Earth. I gather the seafloor is largely made of basalt, but whether anybody has measured the titanium contents to see whether they vary in different places, I don't know. Sorry, I'm not a geologist. I've coughed out of that one.
Okay. If we've got no other questions from around, is that a hand up I can see? Or somebody, oh, just somebody taking a drink, that's all. It's okay, somebody just taking a drink in my peripheral vision, that's all. I think we've worked Peter hard enough tonight. So with that, ladies and gentlemen, will you join me in giving Peter Lloyd a big Mexprin Swinton Astronomical Society thank you. Thank you very much, Peter.
Well, thank you very much for listening.